Hello everybody, this is the third lecture. Today I will speak about the coordinates. We will continue on the vector calculus, chapter 3. My name is Amr Abdul Bari. I am with Electrical and Electronic Department, Nearest University. Last lecture we took the coordinates, the Cartesian coordinates, the cylindrical coordinates, the spherical coordinates. Today we will go deeper on the vector calculus and see some more related calculus to the electromagnetic theory. Okay, this is I think in the book chapter 3. Okay, so the integration, we use some integration over some vectors in the electromagnetic work. So for example, volume integral, it's taking the integral over a volume. So usually you take the integration over one index, one direction, for over x, over L, over y, over z. That's it in the normal integration. In volume, you take integration in a volume. The volume you measure it, as I said before, you measure it in the 3 dimensions. So you take in integration over 3 dimensions. dv maybe dx, dy, dz, or in spherical or cylindrical coordinates, whatever. The line integral, you take integration over one length, over a line, over dx, dy, dz, for example, or the rho, the theta. Line integration maybe, for example, circular or closed or open. This is the meaning of closed. We will come through it later. The integration over the surface, the integration over a surface meaning that you have integration over a square or rectangular, so you have 2 dimensions here. Okay, maybe the surface is open or closed. Okay, now let's take an example. If I have this O, Q, P, T, and I have a point at P, it's at 1, 1, x, y, x1, y1, and we want to evaluate from 0 to p rho square the rho. Okay, so you take here in the cylindrical coordinates rho. Okay, now you may take it over multiple times. For example, rho here, if you calculate rho it's equal to x square plus y square. This is rho square. Maybe rho, it's you take the square root. Now along OB, from here to here, from this point to this point, you take length. You take integration over a length. So you take integration over rho square dl. So dl, it's in the direction of rho. So a rho. This is a rho. This is not ax or a y. This is the direction. And you take rho square d rho from 0 to the square of 2, square root of 2, meaning that I take here, I put 1 square plus 1 square, this is 2, and you take the square root. So from here to here it's 0, the rho giving here the value of 0. The rho at this point, at P point, it is the square root of 2. Now if you take this integration rho to the power 2 to the integration, you will plus 1 and you multiply, divide by the new root, the new power. So it's rho to the power 3 over 3, and it is limited, so it is from 0 to the square root of 2. So if you calculate this one, you find that it is 2 multiplied by square root of 2 over 3 in the direction of rho. Maybe you can convert this direction rho, if as it is in, this is sine, so in direction of a is that ay, it is sine the theta here. Here, because it's a square, so this is 19. This is 19. So this is should be 45, or pi over 4. 19, it is 90. So 90, not 19. Pi over 2. So the divided by 2, this is equal, so this is pi over 4 here, and this one here, this is theta. So the x in the direction of x, you find it as ax cosine. So you can calculate this to find this is the final thing. Now let's see it at the line of OQP. OQP. So you take it over the x and y, these lines. So the x and lines, so you take it as x square y square dl from 0 from O to P, from O to P, from O to Q, from O to Q. This is direction is y square dy. There is 0 x, and in the other direction from Q to P, it is 1 plus x square dx. Okay, so 1 over 3. If you calculate this one, so you put here y square as 1, and from 0 to 1 you calculate y to if you calculate this integration and this integration, this is the results. Along O to B, O T P, then you'll find that you will replace x square 1 plus y square. So this is from 0 to O, this is from O to from O to P, T here, which is 1. From O to B, the length is 1, so it's the same as from 0 to 1. And here it's again from T to B, it is from 0 to 1. This is the result. It is very easy. So this is some integration. We take integration over 1 index, 2 index, 3 index, whatever, over the surface, over the length, differential length, or differential surface, or differential volume. Now let's go to another thing. Let's find that we have here del operator. Many quantities we work with in the del operator. In electromagnetic, we work with vectors. Okay, so vectors have magnitude and directions. We work in magnitude and direction in the space around us, the space, the x, y, z, the coordinates. So every calculation, it is in the coordinates. So this y, we take the vector calculus, and it's chapter 1, 2, 3 chapters in the book. So that's why you have to have a good understanding of the vector calculus. Now we take del operator. It's operator like the multiplication, like the dot product, like the vector product. It is another way of calculation. Now the del operator, you use this one, del. This is a symbol, and it's a vector differential operator. You take the differential integration, or differentiation over one dimension, over 2 dimensions. Okay, so there is 4 of them. I will mention 4 of them. The gradient of a scalar, this is the gradient. You take del without any notes or notation, v. Okay, this is giving you a vector. The result is a vector. The divergence of a vector, it's del dot a. So a dash, which is a vector. So this is giving you a scalar. The result, of course, the curl of a vector, it's del cross a. This is the writing, the notation you should have. This is without dot, this with dot, this with vector. This is giving you the result is of this operation or this calculation is a vector. The last one is the Laplacian. The Laplacian of a scalar, this is a combination, a divergent and a gradient, which giving you again a scalar. Okay, now I will go through each one of them. It's this four operation using the del operator. Okay, now in Cartesian, starting with the gradient, in Cartesian it's taking the differential equation, differential calculation of each one of them. Okay, that's meaning that you take the differentiation over x in the direction of x, differentiation over y in the direction of y, differentiation over over z, partial differential, so in direction of z, so it's the normal partial differential. Okay, this is in Cartesian. In cylindrical or spherical, this is the equation for it. I will not give you the calculus how we reach this through the delta phi or these ones. You may go and search for that. Now let's see the gradient. If I have here, if I have a point P1, and P1 have xy z. Okay, so P1 it's a point xy z, P2 x2z xo. So P1 have a potential. You know that the voltage difference, the difference voltage is a difference between 2 points that have a potential. So V1 and V2. Okay, so V1 at point 1 is at xyz, have a value. This is the potential at point 1. The potential at point 2, it's a very small difference, so it is at there is a small displacement in the space dl, so dx plus dx, a small displacement in the direction of x, a small displacement in the direction of y, a small displacement in the direction of z. Okay, so this component dx dy dz is the component of the L, and dl, as we know, this is the point, so it doesn't have any direction, but dl it's having the direction ax, ay, az. Okay, so now from the calculus we have dv, differential or potential, it's a difference voltage or difference potential v2 minus v1. So from v2 to v1 you take dv, it's the partial differentiation over v in each direction. So you can in each direction, or you multiplication of the dy dx dz. Okay, so you take the differentiation at itself in one side, and you take the dy, which we have it here, the dx dy dz, this displacement in one part here. Okay, so here, as you see here, it's differentiation over v, over the voltage, and here the displacement. Okay, now if I multiply, as I remember, if you remember, ax by ay, ax again, it will give you 1. Yes, ay or ax, sorry, ax multiplied by ay, here it will give you 0, as you remember. So ay multiplied by ax, it give you 0. So this multiplication is only applicable if you multiply one by one. So each one of them will be multiplied in the corresponding one in the direction. So ax, ay, az. Okay, so it will give you this value again. Now let's see here, this one, I will take this one and we will name it as J dash. Okay, so this is J dash, and this one is the DL, the differential displacement. Okay, so dV, the calculus over V, over the potential, it's equal to J dash dot dl. Dot here meaning the dot product, because you make here dot product. Then you can take it as a, if you take the dot product, then you can get j cosine theta dl, if you remember from the dot product. So this is the theta, the angle between both of them, the L and J, the J in its direction. So you can here assume that the maximum value for dl over dv over dl, it is at when theta is 0, which meaning that dl and dj in the same direction, here in the same direction. Okay, now let's name j, which have a magnitude and direction, as delta v. This is the gradient, so we name that j dash is the gradient of v. Okay, so the gradient of v, we take it as this calculation. You take the partial differential equation, this equation, in each direction, and you calculate the v in the partial differential in each value in this direction. Then you get the gradient. Okay, the gradient at any point is constant, is perpendicular to the constant v surface, so it's perpendicular that pass through that point, so it's perpendicular to that point. And the projection in the direction of unit vector AL is dv dot AL, and it's called directional derivative of v along the AL. Okay, this you can maybe you can miss something or you didn't understand, but when you use your hand and solve some problems, then it will maybe very easy. I mean, solving problems in Cartesian coordinates, cylindrical coordinates, and spherical coordinates. You solve some problems in the other coordinates. This is the only way that you can memorize, and not memorize, understand how to solve the gradient, how to make use of the gradients. Okay, now the other one, here we speak about the gradient of a scalar. Now let's go to the divergence, which giving you a scalar. Here the gradient giving you a vector which is perpendicular to the direction which here perpendicular to the surface that pass through the point. Okay, here giving the other one, to the second one is the divergence. Let's go to the divergence. Now let's before speaking about a divergence, let's speak about the surface integral. Now in the gradient we speak about a length integral, a differential length. Here we will assume that we have a surface, this surface, and this surface there is some flux. So we define the surface integral ax y z, define it everywhere in this surface. O and over s is called the flux of A. So the flux A dash or phi, it's the integration over A dash dot an, the direction, ds. ds meaning dxy, dyz, dzx, d rho phi, d phi. What it's the integration over surface. So an here is the direction. You may remember that the direction of the surface is outward unit, so it's perpendicular this here to the surface. So we have a surface, we have a small portion of the surface ds, and you take the integration all over this s. This is the meaning of the flux. Now maybe it is here, if the surface is closed, we do not the flux as with this circle, meaning that this is closed surface. Closed surface, that this is defined within some points. There is integration over this place. You take this surface. Okay, the flux may be negative or positive. So you can the flux here, you can imagine it is the magnetic flux that's come from the north to the in magnetic material, for example. So it's a, you can graphically represent it by some lines, go from the source of this flux and go outside. Okay, so this is what's written here. The magnitude is can be represented by the depth of these lines or the length of the lines. Okay, and the direction in the same direction of these lines. Okay, now as we describe what is a flux, now we describe what is the divergence of the vector. So the divergence of a vector, it's how many or how much flux per volume. Okay, so how much in or out flux that's coming in or out from a zero or a volume that tend to be zero. So the limit of dv to go to zero, so we take the integration, this integration of the flux over dv, then this is the divergence, delta dot a dash. This is the flux. So we name this operator as divergence. Okay, so how we calculate it using this equation. So again, a partial differential over ax only in the direction of x, ay in the direction of y, az in the direction of z. This is in Cartesian, this is in cylindrical, this is in spherical. This is the first question for you: how we get the divergence in the cylindrical coordinates and the spherical coordinates. Prove this. Okay, this is question 1. Now the divergence Gauss theorem: if we have a surface, if we have a volume, this is inside, there is a volume, and there is a closed surface from outside, this surface is, if we have this volume and we have this closed surface, Gauss, some scientists said that the total outward flux over of a vector field A through the closed S, so the flux here go from outside, from this surface. Okay, so we calculate all the lines. We, for example, or for a simple understanding, we calculate how many and how tall all these flux. So all of them, it's equal to, here he said it's equal to, it's the same as the volume integral of the divergence. So I have the divergence here, this one. If I take the volume integration over this, it's the same as the total outward flux. If I take the this is the outward flux, total outward flux of the field. So it is the same as over a closed surface, not an open surface. The same as the integration of the volume. Volume integration or integral over the divergence. This is a theory. Okay, so if there is no divergence, it's if it is a convergence, or it's said to be solenoidal, meaning that delta dot del dot a dash, it is equal to 0, so it is solenoidal. Okay, so this is the divergence. Now let's go to the curl. Where is it? Yes. Now the curl of a vector. Before we go to the curl, I want to show you something in the book. Now let's see here. This is chapter 3. This is the del operator. Yes, the gradient. Divergent. Yes, here this is illustration of the divergence of a vector field at P. This is the point where the volume is converted to 0 to be if it convert to zero, a volume convert to zero, then it will be a point in the space. So this is a diversion. This is the meaning of diversion. Diversion meaning a distribution. If you have, for example, if you have some light source lamp, and the light lines go out from this lamp, yes. So this is an example, an illustration. Imagine that you have a lamp, or you can see it in your home or your area, whatever, in the room that you see this video, this lecture. So you see a lamp, and the lights come outside of this lamp to everywhere. So distribute the lamp, distribute the light here. It's electromagnetic, so distribute everywhere. So this is meaning divergence. So this is called positive divergence, because it's go outside of, or outward, the flux go outward of the point. Here negative divergence, meaning that it is go inside, negative, to go inward the point. Here it's zero divergence, because it's not diverge, it's not related to this point. This is not a source of this point. Okay, so this is an illustration in this book. I stuck with a book, or trying to giving you some illustration, so you can, if you read the book, or if you read something from it, then you will understand more better the illustration here. And if you read the words or the paragraphs under, you will make more understanding. Now let's go to the curl. The curl of a vector, if I have net outward of a flux through a surface bounding a volume, indicating the presence of a source. As I said, if there is a light in the room, meaning that there is a source, there is a lamp in this room. Okay, and the divergence measure the strength, measure how much, or how dense this flow of this source. Okay, this is giving you a scalar. Now if I have another type of sources, there is another type of sources here, which is, we call it vortex source, causing a circulation of the vector around it. So the vector go around and somehow circular around the source. So the circulation of A, it's meaning they take the circular integral over A dot delta L of if you have a closed path. Okay, now the curl, you take this circular over the delta S. Okay, so it's a rotational vector, so it's giving you a vector, and the magnitude is the maximum circulation per unit area, where the area tend to be zero, so it will be point again. Now the direction of the area is the direction of the area, it's going outside of the area, it's AN. Okay, so here we will apply the right hand rule to find the direction. Okay, so the curl of A over X, it meaning that the area of X, it means that you take the partial differentiation over AZ, or the partial differentiation delta AZ or divided by delta Y, and delta AY over delta Z, and in each one you take the other two. So that's you can understand this. So here I take it over the delta Z. Okay, X, sorry, curl of AX in the AX. So you take it AZ and AY, each one you take the differential equation the other dimension. So curl of A Y in the surface of Y, you take the differential equation of Z of for Z of Z for AX minus differentiation equation for delta X for AZ, the other one. You see, this is here and here, and this is here and here. This is I trying to make some sense. I know this is a calculation and there is a proof for all of this, but some of them you don't have to prove everything. You just have some meanings about how we represent the phenomena, the physical phenomena, in using the mathematical way. Okay, now this we can simply use, if you remember the cross product. This is a cross product. If I may review, as you here have ax, ay, az. If you remember, if we cross product a, cross product b, you remember what we do? We just take each part of a, put it here, ax, ay, az, and b, px, py, pz. Take it as like this. Here we have the del, which have x, y, z, but here del it's differentiation, and here we have ax, ay, az. So in each direction you just take the two partial differentiation in the other two. So if you take in the ax direction, then you take the partial differentiation of y for az, and of z the partial differential of z for ay. This is like this. You solve this matrix for each one of them. Okay, now that's in cylindrical, of course, in cylindrical coordinates, of course, but it's having the 1 over rho from outside here, rho. So the second question today, I want you to go and search and prove how we got this one for cylindrical and for spherical. How we got this? Okay, why we put r sine theta here, or r multiplied by a theta here. So this is the second question. Okay, now let's see another theorem. We took before one theorem, Gauss theorem or divergence theorem. Now we have Stokes theorem. Here he said that if we have some area like this one and it's closed, so there is a line path outside that's closing this area, surface, sorry, let's be more specific with the words. So open surface bounded by a closed path, C, closed path. The vector area it's in outside. Okay, so he said that the circulation of a vector field A around the closed path, if you take the each dl, and you take the integration over this line, over this differential length, circulation, because it's your circle around the surface, it is the same if you take the surface integral over the curl. So you calculate the curl, this curl, you calculate the curl, and then you take the surface integration over ds. Okay, then it is equal to each other, the same integration it's hold. Okay, so some condition, if you have 0, the curl is 0, then the vector is called to be irrational or conservative field. Okay, so we have here some other two fields or other names, irrational or conservative. If the curl is 0, for a scalar v, meaning that you take the curl of a gradient. So the gradient here, this is a scalar. So we mean here that we take only the curl of the a vector. That's with giving us some value. If again the curl is 0, then the other side is 0. If you take the scale, the closed loop of the length of the line that the closed path around the surface, 0. Okay, it's meaningful because you take a length around the scalar, around the point, so the length is 0. So you didn't have any area to calculate. Okay, now another theorem, Helmholtz theorem. He said that a vector field is determined within an additive constant if both its divergence and its curl is specified. So that's meaning that the curl and divergent you have, then you can name that this vector is determined within an additive constant. Okay, so I know that, again I will say it again and again and again, there is a lot of things that may be not understandable, not imaginable, so but you can easily imagine that using the when we speak more about the physical phenomena. Let's see here what's the curve. So in the book here, this is meaning of divergence of from outside of a volume, so each point will go outside. Now the curve here, this is the point and this is the closed area, rotational nature. Okay, so here, as you see here, this is the illustration of the curve. Here this is the point, and the curve at points out of the page. So imagine that this is the screen of your laptop, of your phone, and if you put your hand or your fingers on the screen, your thumb will go outside the screen. Yes, so because your hands will move it in this direction, in a curl direction, so you will move it to, if you the screen in front of you, then you will move it to the left side of the screen, then your thumb will point to you, towards you, to outward of the screen. Of course, if the other side, then that's meaning that your thumb is toward that screen, your thumb not pointing at you, it's pointing out on the screen inside. This here curl is 0 because it's not rotational, so there is something we can calculate the integration. Okay, this is the basic meaning, or a very basic illustration about the curl, about the divergent, about the gradient. I know there is the last one. Yes, here the last one is the Laplacian of a scalar. The Laplacian meaning that we take two calculation. It is the divergent of the gradient. You remember the gradient here. This is the gradient. You take the Laplace, the differential equation over each one of them, and in each direction. And here you take the differentiation, the partial differentiation in each direction. Then it's like you take the second partial differential. Okay, you multiply each one of them. So that's why we take the del to the power 2. So this is meaning of the Laplacian. Okay, Laplacian giving you a scalar, another scalar field. Okay, this is the last one. So what I speak about today is for in the vector calculus, we take 4 different operation, 4 different calculation over the field, over the volume, over all of them is related to the electromagnetic in somehow. Maybe later in the later lectures you will figure out why we take all of this, why we calculate for each field we take different fields. The third question today, I specified 2 questions before. The third question today, I mentioned some type of fields. Yes, I mentioned a rotational field or rotational vector. What is meaning by that? So I want to look and search and read and try to illustrate using your words or using your hand in illustration, different fields. What is the different fields, and what is the difference between them? Okay, and give me an example from the physical phenomena, from the real world. What is that meaning in the real world? Okay, these different fields, that's how we represent it in vectors, and we take this calculation over these vectors, okay, using the mathematical representation. That's it for today. Thank you for listening.